All right, this is Dr. Ali Mughebel. Before we speak about block codes, let's recall where the coding is implemented in a communication system. So the slide title says coding position on a transmission system. We have the digital source, we have the source encoder. A source encoder will do the compression. Then we have the channel encoder. Then we have the modulator, the channel, the demodulator. And then we have the channel decoder. And then we go back to the source decoder, which do the expansion of the data. So these two blocks in blue shows you the location or the position of the coding in a communication system. To achieve shallow capacity, to get close to capacity, to make use of the system, we need coding. If your system is very simple and you have enough bandwidth and just point to point, maybe you don't need this block. We have different types of coding. We have block codes and we have convolutional codes. These are the two main categories. Under block codes, you'll have different names, different codes like Goulet code, parity, Hamming, BCH, and Reed-Solomon codes, RS, and others. Under convolutional codes, you have also other convolutional codes which are systematic or non-systematic. And we have extension of these or concatenations, which are the turbo codes, LDBC codes, and trellis codes. Of course, other techniques are also there. Now let's focus on block codes. Block codes, in block codes, the data is parsed into uniform k bits. So I have a sequence of data. I will just take k of them. These are the information. Every k, we have information bits. So this makes the number of valid possible information bits 2 raised to power k. I'm going to add to them. The coder will add n minus k. So the total length is n. The added here is r, which is equal to n minus k. N is the total length of the code word after coding, and k is the information bit. So we have n minus k check bits. An n bit block is transmitted. This is the n bit code transmitted, and the coder will be assumed to be memoryless, which means that we deal with one block at a time and they are disconnected. They are having no relation to do with each other. So we're just dealing with one block at a time. The transmitted data rate is going to be the original data rate or the required new transmission. If we are having RB, then we need now to transmit for the same data the new R sub C. C stands for the code. Is going to be more. RC is more than RB, and the ratio is n over k. For every k bits, we need to transmit n now. So this is the original required information rate, and here is the coded rate to maintain the same information. So redundant bits are used to detect or correct errors. Those redundant bits are used to detect or correct the errors. So if we deal with the data as blocks, we call it block codes. So block codes, we have different types of block codes. We have Hamming, Goulet, BCH, Reed-Solomon, maximum length, checksum, cyclic redundancy, and just name them, a lot of them. And maybe in this presentation, our objective is not to remember all of them, but just to get an idea that this is a field where people develop codes. Now, depending on the amount of redundancy added, block codes may be used to detect only errors, or they could also help in correcting errors. So the more check bits will allow us to correct bits as we get errors. So if you recall, we have errors that are random and error that occurs in bursts. So block codes correct burst error, adjacent errors, as well as random errors. Usual block size is 64 to 2048. That's the usual range of size. We take 64 bits together up to 2048. It could be, of course, more or less, but we're just speaking about the usual range of numbers. Now, in comparison with block codes, we have something called convolutional codes. When it comes to the performance and error, block codes may be not as good, as powerful as convolutional codes, but of course they have their own advantages, being simple. The table on the side gives some examples for burst error correction code block codes. And here is the code N to K. The first number represents N, the second number represents K. So the number of parity check bits is the first number minus the second number. 7 minus 3 is 4, 15 minus 9 is 6, and so on. Here tells you how much is the length of continuous or burst error correcting capability. This can correct 2, 3, 4, 4, 5. Of course, as the size increases, as a number of check bits increases, we have more to do. So the last column shows you the code rate, which is the first number here divided by the second number. So these are easily can be induced from the first column, these two. Here's a subtraction, and this is just the ratio. An example of a 7-4 Hamming code. The Hamming code was developed by Bell Labs in 1940s, and it is a 7-4. For every 4 bits we generate 7 bits of code. So the number of valid code words is 2 raised to the power 4, which is 16 valid code words. And in total, the possibility that we have is 2 raised to the power 7, which is 128. So only 16 of 128 possibilities are valid. The table shows you here the message, the associated code words, and the message, the associated code words. So we'll also show the weight of the code word, which is the number of ones. So 0, 3, 4 ones, and so on. So if you want to encode, you take 4 bits and find the proper code in front of them and send the code rather than sending the original data. This is a very popular example, which is a 7-4 Hamming code. Another example for block codes is the Goulet code. It's a different code, different generation technique. Let's go over these examples just because they are used in satellite application. As, for example, here we have 2312 cyclic code. What do we mean by cyclic codes? Cyclic codes are if you rotate any single code word, like you take this bit here, and of course it's a cyclic, it's a cycle, so this one goes back here. You will find that this is also a valid code word. So a cyclic code word, every cyclic shift of a code word is a valid code word. This has a D minimum of 7, the minimum distance of 7. We have talked about dmin in the previous video, and also we'll talk this at a coming video. It's related to the performance. So we have 2412 cyclic code with dmin equal to 8, and of course rate here. This is more efficient. This is more efficient, but this one is maybe more simple to think of because for every bit there are 2 bits, so the rate is 1/2, and the minimum distance is 8. Rate 1/2 is easier to deal. This code is easier to implement, and it simplifies the clock synchronization because it's just doubling. Goulet codes and the single error correcting code Hamming codes are perfect code. So this is an example of a perfect code. Means if it corrects a certain number of pattern, then it will, if it corrects 2 errors or 3 errors, then all of them will be corrected. So there aren't like certain patterns that are correctable and others that are not correctable with the same number of errors. We can define perfect codes as all possible patterns of a given number of errors are correctable. So if it corrects a given 2 errors, it will correct all 2 errors. Goulet codes are used for digital broadcasting, satellite TV, computer memories also. The Goulet codes has been used in various applications, including satellite and space communication, digital storage systems, and error correcting memory systems. Reed-Solomon codes are used for compact CD. This is a different type of code. I just want to mention here the important ones. Okay, so we have explained the meaning of, we touched on some examples of Goulet codes. We defined cyclic codes, perfect codes, and also we have we are showing here an example of an encoder of cyclic code where the data bits come from here and the parity bits come from the other circuits. This is an example of generation of cyclic code. Now let's move to convolutional codes. Convolutional codes provide simple encoding structure and widely used in satellite links. So convolutional codes are not block codes in general. They don't take blocks and then encode them. It's a continuous process. For example, you see here in the circuit, the input will come as a stream, and as a stream gets in, here we are showing one arrow, so there is only one bit. Another stream will get at the output. So we have two here. We take one from up, one from down, and so on. So here I rate 1/2 code, and it's a continuous process. It's not, we don't take blocks here. So convolution codes provide better error correction compared with block codes at low signal to noise ratio, especially at low signal to noise ratio, they are better. They use constraint length. So let's look at the block code, at the convolutional code. The circuit here is showing you a simple convolutional encoder, and the switch here changes state at each input clock. So we take 2 per 1. Other systems could have multiple inputs in parallel. So we have small k is the number of concurrent inputs. V is the number of outputs, and of course k divided by V now is the code rate. While capital K represents the memory size, because the way we generate the code is that we keep track of the data. For example, here we have 3-stage shift register, which means capital K, number of shift registers, or we call it span, or constraint length is 3. We keep the sequence, we XOR and generate the bits. So the first output here at the up is the XOR of 3 bits, while the lower one is the XOR of the first and the third. There is no connection here. So this is how we generate the bits. Of course, we have to clock the system. This is the bit clock, so that it works every time. So we know the meaning of constraint length or span. It's the memory size or window length. We mentioned that convolutional codes have fairly high gain. Turbo codes are even higher gains. Turbo codes we'll talk about them. Turbo codes are built on convolutional codes. This is why we are mentioning them here. Okay, so don't handle burst error very well. These are part of their characteristics. Convolutional codes are generally generated by a tabbed shift register and 2 or more modulo 2 additions, as we explained, which are fed in a backward network. So we are feeding back this, and we have the network. This is how we generate them. Why do we call them convolutional codes? Do you have an answer for that? If yes, write your answer in the comment section. Only specific state transitions and output are possible. So what makes this a code is that this circuit is going to limit the relation between the bits. So not every input generates all possible outputs. So only specific state transitions and outputs are possible. How do we check for whether this sequence is valid or not? It's not as simple as block codes. We need to use decoding algorithms, like the decoder detects errors, correct them to the closest possible track, like the Viterbi or Viterbi algorithm. Viterbi is the name of a scientist. So convolutional codes are also known as Viterbi codes, because usually we are using Viterbi code as a decoder. Okay, so this slide introduces convolutional codes, explain the variables, the rate, the constraint length, and the span. And of course, we touched on some of the properties of convolutional codes. Now, more examples, just to give you an idea about the convolutional code performance, although later on we are going to touch more on the performance. So first, in the lower, you see 2 examples of possible connections. This is similar to the one that we had before, but we're showing you the modulo 2 operations and the flip-flops. Other possible operations, like for example, here we have, we take 2 inputs, so small k is 2, and the output V is 3. So rate 2/3 here code. And I would like also to note that we have here the performance of an example. I will come to this. So these are just 2 examples. The coding gain in dB for various Viterbi codes or convolutional codes. You can see here that this is the bit error rate. This is the required EB over N naught for the uncoded system, the amount of energy you need to put. And this is our different code rates: 1/3, 1/2, 2/3, 1/3/4. Of course, as you go to the left, you have a stronger code, but costs more. And then, of course, capital K represents the memory span. Of course, the longer the span, you expect higher gain. So if you go this way within the block, you expect the coding gain to increase. So the maximum here maybe is 7.3. Okay, this at the requirement for different probability of errors. So the coding gain here is 6.5, 5.9, 4.4, and you can look at the number. This is like only requiring 1/4 of the power. Okay, so this is for rate 1/2. We have all the numbers. Okay, those are the amount of gain that you get. Of course, for 3/4 you expect the number to be lower in general. Fantastic. Now this is reflected here on the diagram where we show the probability of error and the energy EB over N naught. Of course, this is the performance of rate 1/2 convolutional codes with constraint length from 3 to 8 and 32 bits path. So we have this is regarding the decoding, just forget it for now. So we have 3 to 8 constraint length. So as you increase the constraint, the memory, of course the performance improves dramatically. As you can see here, we're going for a given 10 raised to the power -3, for example. You can see the difference in coding gain between having k equal to 3 and k equal to 8 or 5 and 7. So there's a big gain by increasing the memory. But of course, the decoding becomes more complicated. Now let's talk about code performance in general. We have we talked about we touched on the performance of convolutional codes, and we showed some examples. But if we talk about in general, we need to classify codes into linear or non-linear. If it's linear, then all 0 code words are valid or is a valid code word. We also have systematic codes and non-systematic codes. In systematic codes, the information appears as is, as part of the code. We have perfect codes and non-perfect codes. We explained all of them. In perfect codes, the probability of BER can be evaluated exactly because we know exactly what errors are corrected or not. However, in non-perfect codes, we cannot find BER easily. We need to use upper or lower bounds because some errors are corrected, some double errors are not corrected, or triple errors, and so on. So code performance can be evaluated based on full weight distribution. I give you all the code words with all distributions, and you can find what's the probability on how many errors required to go from one to another. But this is difficult. So usually we go into the minimum, the bottleneck, D minimum, to evaluate the code performance. We look at D minimum. Remember that in code with minimum distance D min, the number of detectable errors is D min minus 1, and the number of correctable errors is D min minus 1 divided by 2. Of course, you take the floor if you have fraction. Burst error correction is important, although we speak here in general as we deal with random errors, but burst error performance is important because there are typical problems in real life where errors occur in bursts. Here's just showing you an example when we talk about different classification. So linear codes, cyclic codes are example of linear codes, and then we have BCH as an example of a specific code, example of cyclic, that's linear. So you can have some Venn diagram that represent the relation between different type of codes. Let's look now at the performance of error correcting codes through the example here. In the diagram we show here, we show the probability, the bit error rate, and on this axis we show the EB over naught, the energy. So you'll have to have the minimum. You'd like to be in this corner because you have minimum error and less power, or less EB over N naught, energy per bit divided by the noise power, spectral density. So let's define the coding gain. The coding gain tells you how much reduction in EB over N naught while maintaining a given probability of error. Let's take an example. With BCH 127 to 64, which is shown in this line here, this is the indicator, this is the performance. We need 7 dB to get 10 raised to the power minus 5. So if you draw a line from 10 raised to the power minus 6 here, it will give you 7. So this number is 7 to get 10 raised to the power minus 6 without coding. If you decide, with coding, if you decide to not use coding, then it's going to be just continue the line. This line is the uncoded binary phase shift keying. So see how much is the difference here to go from here to here. I'm drawing this in the line. So this line is, you subtract 10.6 from 7 and you get the coding gain. But be careful, this is not pure gain, because when we did coding, we have changed the rate of transmission, and that affects the bandwidth, and the bandwidth, of course, results in reduction in carrier to noise ratio, and finally EB over naught. So to sum up, I would like you to notice that there is a direct gain, coding gain, because of the coding, but there is also a cost you have to account for. Another example, this is important because some people just get tricked by this is how much you gain by doing coding. There is also a cost. So you have to account for both. Another example using rate 1/2. I'm showing the second example with blue so you don't get confused. So this is the rate 1/2 convolutional encoder. Okay, if you you draw the line here, it will cross, you draw the line, you get a certain requirement in energy. If you compare it with the uncoded system, which is up to here, then you get the amount of gain to be 6 dB. So approximately from here to here is 6 dB. So coding gain, but it requires, of course, doubling again B and increasing signal to noise ratio, carrier to noise ratio by a factor of 3 dB. Because we have lost 1/2 here. So 1/2 in the coding rate, which is doubling, so which is 3 dB. So 6 dB gain, 3 dB cost. So the result would be the net benefit is 3 dB. Please freeze this slide and make sure that you understand the details. An example from satellite. In satellite TMDA system, a 127 to 113 code is used. BCH double error correcting code is used in 120 megabit transmission system. So this is just to give you an idea about some of the realistic examples used for satellite communication. Okay, now let me leave you with a quiz with some test of your understanding. The first question is, block codes can achieve a larger coding gain than convolutional codes or coding. Is that true or false? A or B? Please write your answer in the comment section. 1, A or B. The second question is, which of the following indicates the number of input bits that the current output is dependent upon? So the current output will depend on how many inputs? This is determined by the constraint length, code length, search window, or information rate. Think, and then indicate your answer in the comment section. The third question is related to calculation. In a satellite link with transmission rate of 10 kilobits per second, a block code is used with dmin equal to 4. Now, how many errors can this code detect? How many errors can this code correct? And now, if a block size of 10 is used, now we have coding with block size 10, and probability of bit error equal to 10 raised to the power minus 2, that's the crossover probability. That's, of course, large error, but we are just trying to learn the calculation. With the above code for error detection, we're using now block size of 10 with this code. What is the probability for error being undetected? Or sorry, for an error being detected? So now you know the block length. You need to find how many bits can be an error so that we can detect the error. That might take some time, so I'll leave you with enjoyable time. You can freeze the video now and do the calculation and share your answers for all the questions in the comment section 1, 2, and 3. See you then. Thank you very much.